Geography has always placed importance on relationships between locations. Indeed, Tobler's first law of geography states that everything is related to everything else, but near things are more related than distant things. The concept of spatial dependence is certainly at the core of spatial analysis. But interestingly, it wasn't geography that advanced the use of spatial statistics and cluster detection, either in space or space and time. Rather, it was other disciplines such as epidemiology and econometrics that saw the need for methods to analyse patterns in data. Cluster analysis is now used in many disciplines for many different purposes. It's used to identify the locations of clusters and to examine what may have led to those patterns, by looking at the locations in relation to other data and exploring possible contributing factors. In 1865, in London, John Snow thought that cholera might be transmitted in water rather than air. Now, this was against the popular belief of the time. For his analysis, rather than using a standard time series to plot the data, he marked deaths on a map, along with the locations of the area's 11 community pumping wells. The map revealed a story that showed an association between cholera and the proximity with the Broad Street pump. And importantly, he set it in a context with other local water sources and surrounding areas without cholera. Fundamental to analysis is the comparison to answer the question, compared to what? The map that John Snow created presented clues for comparison between the living and the dead. This was strikingly visible at a brewery and at a workhouse. None of the 70 brewery workers actually contracted cholera, so they were allowed a free amount of malted liquor every day, and there was also a deep well within the brewery. They were saved by their own beer. There was also a workhouse in Poland Street that was surrounded by houses in which there were many cholera deaths. Yet of the 535 inmates at the workhouse, only 5 of them died. The workhouse had its own pump on the premises, and they didn't use the Broad Street pump. Snow's analytical approach, through exploring the geography of the deaths and searching for comparisons, revealed the real cause of cholera. Looking at maps of distributions, you can start to draw conclusions, but often the patterns are more complex and you need help to find out more information. By using statistics, you can look at the assumptions and explore your observations. Inferential statistics can be used to test various hypotheses. That's often used as a basis for decision making. The approach can be used to evaluate whether a dataset as a whole is clustered, for example using global Moran's eye, or whether clustering can be seen within the dataset using local Moran's eye. Both these tests are testing for spatial autocorrelation, under the assumption that the attribute being analysed is randomly distributed among the features in your study area. So spatial autocorrelation is a measure of similarity of objects within an area. It's the degree to which a spatial phenomena is correlated to itself in space, hence the term auto. When looking at spatial associations, geographers often need to understand whether a spatial distribution differs significantly from the outcome of a random process. That's so they don't attribute a pattern that they see to something that's actually random. You might also be interested in finding locations where there's both high and low values in close proximity, to identify where there's areas of high incidence of crime or rivers deep, mountains high. The Gettys-Org GI star, which is also known as hotspot analysis, identifies statistically significant clusters of high values, hotspots, and low values, cold spots, comparing the neighbourhood values to the study area. The hotspot term is used broadly to indicate some kind of spatial clustering, irrespective of the approach that you use. But then again, it's also used with reference to a wireless internet connection, a popular place, and logically enough, a small area that has a relatively hot temperature compared to its surroundings. You might also be interested in exploring patterns over time. Including time in your analysis can introduce more factors for you to consider. There are a number of different ways that you can consider time in your analysis. You can use a snapshot or a summary of time. You can cycle through the data looking at recurring time periods, such as days, months, or years. You can look at time trends and compare changes over time, such as watching the expansion of a city. Or you can look at before and after events, such as before and after a hurricane. At its simplest level, comparing change over time looking at snapshots of it often means repeating your analysis for each time period of interest. Learning to write scripts and create models allows you to automate that process. This is a really valuable skill, allowing you to correctly repeat each of those tasks. Of course, that's going to save you a lot of time, and it also has the advantage that you're documenting your workflow as you go. The ability to map changes over time can be visually explored, and in some cases, animation might be useful. Patterns and trends are important in your data, but so are outliers, missing data, or erroneous data. So the more you know about your data, for example, anything that may have happened in the past, any known issues in that data, means the better you'll understand what you're working with and the results you would expect from using that data. The input directly affects the output. The better you can interpret your results, the more confident you'll be about the findings that you have. But it's also important to think about communicating your results and interpreting them. There might be hidden variables, hidden data that you didn't include in your analysis, unknown variables that are affecting the patterns that you see. As a geoanalyst, it's a good approach to be a little cautious.